This session discusses the stability analysis of nonlinear systems using describing function approach. Let us start with a linear system. The block diagram representation of a linear closed loop system is shown in the figure. Here, the open loop transfer function is GSHS and the closed loop transfer function is C of S by R of S is equal to G of S by 1 plus GSHS. If you consider a unity feedback system, then H of S will be equal to 1. Hence, in that case, we can write the closed loop transfer function as G of S by 1 plus Gs. As far as a closed loop transfer function is concerned, the denominator polynomial is called the characteristic polynomial, and 1 plus GSHS or 1 plus Gs, depending on whether you have a unity feedback system or not, equal to 0 will give you the characteristic equation. This results in G of S is equal to minus 1. Minus 1 can be thought as a point minus 1 plus J0 in the S plane. This point can be obtained by rotating a unit vector from the reference axis through an angle of minus 180 degree. That is 180 degree in the clockwise direction. Hence, minus 1 plus J0 point, that is this point, can be written in the polar form as 1 angle minus 180 degree. Hence, we are interested in the value of G of S. This is the reason why we draw the open loop transfer function G of S and set the margin of stability as magnitude equal to 1, that is 20 log 1 equal to 0 dB, and phase equal to minus 180 degree for gain crossover frequency and phase crossover frequency respectively in the border plots. Here we identify the closed loop stability in terms of open loop transfer function plots. The significance of the critical point minus 1 plus J0 in Nyquist stability criterion also arises from this concept. The stability analysis of nonlinear systems using describing function also has close similarity with the stability analysis of linear systems using Nyquist stability criterion. Let us consider the closed loop system shown in the figure, which has a nonlinear element whose describing function is given as Kn of x and a linear element whose transfer function is given as G of s. Representation of Kn of x in the block diagram and treating this as a linear function holds good because describing function is a linearization approach. Hence, we can consider the nonlinear element as a linear element. Thus, Kn of x can be combined along with G of s and a transfer function can be obtained. In this case, the closed loop transfer function is given by Kn of x into G of s divided by 1 plus Kn of x into G of s. As mentioned in the previous case, the characteristic equation is 1 plus Kn of x into G of s is equal to 0. This gives you G of s as minus 1 by Kn of x. Here it is assumed that the input to the nonlinearity is always a pure sinusoid x is equal to capital X sin omega t because of the low pass characteristics of G of s associated with it. For different values of initial conditions, a signal of the form x is equal to capital X sin omega t will be generated at the input of this odd symmetric or odd half-wave symmetric nonlinearity. And for this it is required that small r equal to 0, which is the reference. We can say that unlike the critical point in the Nyquist stability criterion, we have a critical locus. That is because we have G of s is equal to minus 1 by Kn of x. Thus, the critical locus is minus 1 by Kn of x, where x varies from 0 to infinity. In order to discuss the describing function approach for stability analysis, we need to plot two diagrams. One is the G of j omega plot and another is minus 1 by kn of x plot. G of j omega plot is nothing but the polar plot with omega varying from 0 to infinity. Sometimes it is also called Nyquist plot when we draw it from minus infinity to infinity. Minus 1 by kn of x plot is obtained for x varying from 0 to infinity. In the stability analysis, G of j omega plot is superimposed on minus 1 by kn of x plot. We can see that G of j omega as well as minus 1 by kn of x are complex numbers for different values of omega and x respectively. As mentioned previously, the describing function method for stability analysis of a nonlinear system resembles closely to the stability analysis method of a linear system by Nyquist stability approach. In the Nyquist stability criterion, we find the number of encirclements of the critical point minus 1 plus j0. Here, what we do is, instead of a critical point, we have a critical locus. Thus, the relative position of the two plots are very important. That is, the G of j omega plot as well as the minus 1 by kn of x plot in determining the stability of the nonlinear system. When the critical points of minus 1 by kn of x lie to the left of the polar plot as omega varies from 0 to infinity, then we have a closed loop system which is stable. If the critical points of minus 1 by kn of x lie towards the right half of the G of j omega plot as omega varies from 0 to infinity, then we have a closed loop unstable system. A better picture can be obtained like this. Let us assume a person is moving on the G of j omega plot as omega varies from 0 to infinity. That is, a person is moving in this direction. Towards his right we have the unstable region and towards his left we have a stable region. The meeting point of the G of j omega plot and minus 1 by kn of x plot is a limit cycle point. That is, as far as this figure is concerned, it meets at capital A. This corresponds to a point capital A with magnitude as x2 for the limit cycle oscillation and frequency as omega 2 for the corresponding limit cycle oscillation. The system is unstable for capital X less than x2, since those points will be in the unstable region, and stable for capital X greater than x2, that is for the region of minus 1 by kn of x in the unshaded portion. Now we shall discuss the stability of the limit cycle. Consider the system operating at the point A, which is a limit cycle. Assume that a small disturbance is given to the system so that the input to the nonlinearity increases to capital X3. That is, the operating point shifts to capital B from A. Now we can see that since B is in the region of a stable operation, the amplitude of the input to the nonlinear element progressively decreases, because we have seen that a stable operation corresponds to decaying magnitudes. Hence the operating point moves back to A. Similarly, a perturbation which decreases the amplitude of the input of the nonlinearity shifts the operating point from A to C, which lies in the unstable region. We can see that the input amplitude progressively increases due to the unstable region and the operating point gradually increases its magnitude and it moves back to A. Hence, any disturbance either in towards B or C will bring the state back to A. Hence, we can say that capital A represents a stable limit cycle. Here, two more examples are shown. We have two limit cycles in each case. Let us consider the first one. As far as G of j omega plot is considered here, the right side of the plot of G of j omega as omega varies from 0 to infinity, is an unstable region. Let us assume that the system is initially operating at A. Let us assume that a small change in the input to the nonlinearity results in the operating point being shifted to B. Since this represents a stable region, we can see that the operating point shifts back to A with a lesser magnitude of x. Similarly, if the operating point shifts to C, as it lies in the unstable region, the magnitude of the input to the nonlinearity will increase and it moves back to A. Hence, capital A can be thought as a stable limit cycle because any change in the operating point will bring the system back to A. Let us consider another point P, which is a limit cycle. Here, when the input to the nonlinearity increases in its magnitude, let us assume it shifts to Q. Since this is an unstable region, we can see that the magnitude will keep on increasing. It will never move back to capital P. Similarly, if the input to the nonlinearity is decreased at the operating time when the system is at P, let us assume the system is moved back to R. Since it is a stable region, we can see that the magnitude will still decrease. Any change from capital P will not bring the system back to P. Hence, we can say capital P is an unstable limit cycle. Thinking in similar lines, we can see that in the second figure, P represents a stable limit cycle and Q represents an unstable limit cycle.